Hey, good morning. Today, I'm going to continue on our last example on acceleration. We're almost done. Then we are going to do a new topic, which is mass moment of inertia. And this can be found in chapter 17. Okay. So just to recap very quickly where we were before in our last example, we were dealing with this problem over here. Okay. And then we are breaking them into components. Okay, so we have this expression over here where the last time where we stop. Okay, I'm going to continue over here. Please move. Okay, good. Okay, we're going to continue over here. Just to give you a reference, the example we are dealing is this example over here. Oh, this is no good. Okay, what's this example? So just to quickly recap, we would like to find what is our alpha AB. Okay, we'd like to find what's our alpha AB. So by looking at the first equation that we have on top, okay, we have broken down to I component. That's where we got 0.886 minus 103,765. And then we have J 3.732 alpha AB, so in I. And then we have the 67.062. Okay. Then the next one we go for is we look at the J component. So we have 0.5 ABT. So this is done. Minus 179.721. This is done. And then we have minus 7. This is good. Plus by 3 alpha AB. And this is good. And this is minus 83.425. This is good. Okay. So I'm going to equate the J components also in terms of ABT. So acceleration of point B in the tangential direction, this will be equal to minus 7 plus by 3 alpha AB minus by 83.425 and then plus by 179.721, and then this we can divide by 0.5. Okay. So 3 6 alpha AB, and then minus 7 minus 83.425 plus by 179.721. I get 178.592. Let me do it again. Yep, 178.592. So the last equation that we have over here, I'm going to call this equation number 3. And then this is equation number 4. And then if we're going to equate, we're going to equate equation 3 and 4. We will have an expression of 4.309 alpha AB minus by 42.382. And this will be equal to 6 alpha AB plus by 178.592. Okay. So we will have 4.309 309 minus 6 is equal to minus 1.691, okay, alpha AB. And this will be equal to 178.592 plus 2.382. 220.974. Okay. And then finally, alpha AB will be equal to 220.974 divided by 1.691 minus 130.677 radians per second squared. The minus means our assumed direction was wrong. To make it positive, or the correct direction is this way. Originally, we assume it to be in a what? Anti-clockwise direction. Okay. So just to quickly summarize, as I said, this is one of the oh shoot, did I record? Okay. As I said, this is one of the worst example that you can get in a question. Okay. And the most important thing to take note is this. Okay, the most important thing to highlight is this. Okay, I'm going to expand this diagram. This is no good. The most important thing to take note is this. Okay, is that the AB, use a different color. The AB in the normal direction, okay, is towards the center of curvature. Okay, it's not towards point A. Okay, I used to make a lot of mistakes. I assume it to be towards point A because this will affect your ABN, which is equal to V squared over R. What is this radius to take? Okay, so if it's at point O, right, the radius is equal to what? 2 feet. Are we clear? Okay, so that's the most critical component. I'm going to do one more example. Okay, if you look at it, that example, you say, is that it? Okay, it's really straightforward. As I said, decided to show you the worst. Then when we do something easier, it's not that bad. Okay, so the last example that we are going to do, okay, is this one. Initially, you look at it, you might say, whoa, that does not look easy. I'll bet you this is so easy. Right. So this is example, the last example for today. At this given instant, the gear rack have the velocity and acceleration shown. Okay, I think we started this problem a bit. Okay, and I got excited. I went to the difficult one. Determine the acceleration at point B. Okay. So first of all, we're going to draw our transformation. Then we do velocity, or we draw the velocity and acceleration on the gear. Okay. So we understand, we know that this is point A. And we want to find what is going on at point B. Okay. But we are given that we have a acceleration and velocity going down this way. Okay. So acceleration is equal to 3 feet per second squared. And we are given the velocity over here is 2 feet per second. Directly opposite, we are given an acceleration of 2 feet per second squared and a velocity over here of 6 feet per second. Okay. So if we were to continue drawing our components, okay, so over here, I decided to call this our point C. And over here, I decided to call this our point D. Okay, so we have a point C there and a point D there. And because we have an acceleration component, we know that over here, we have a AC normal direction, okay, pointing towards the center. And then the other side, we have AD also pointing towards the center. And likewise, over here, we know if this is in motion, we know that point B, this is in the normal direction. Okay. From here, we're going to put a velocity of point B in that direction, okay? And we are also going to quote that ABT is going in the tangential form, is going at that direction, okay? So now we are going to assume, okay? Before I assume, okay, so omega A or omega, okay, direction is assumed to be going in a clockwise direction. And this is purely because velocity at point C is greater than velocity at point D. Okay. I'm going to make the assumption. Okay. I'm going to make the assumption. Are you all comfortable with the assumption? Right? This is because velocity of velocity of D is 2 feet, and velocity at point C is what? 6 feet. Okay, so we're going to assume. So over here, I think it's a very logical assumption because VC is greater than what? VD. Okay, VC, we know it's 6. 6 is greater than 2. Yes? Okay. Do not memorize, right? Based on understanding. I think that's better to learn. So the formula that we're going to use first, okay? And again, omega, I'm going to assume, okay, again, we're going to assume alpha, not omega, alpha going in that direction. Now, over here, the alpha going in that direction, this is really assumed. Don't know why yet. I just going to follow that direction. If it's wrong, later on when we break into the component, right, it will tell us whether the assumption is right or wrong. Okay. So a lot of times, for this case, we want to find out what is going on at point B. If you look at the question, okay, we have to determine the acceleration at point B. Okay, we have to. But before we determine our acceleration, we know that omega and alpha are unknown. Okay, we don't know that.